Quaternions are a four-dimensional number system, meaning each individual quaternion consists of four real number parts, like what you see on the upper left here. And one of the main use cases for quaternions is that they give us a really useful language for describing and for computing orientation and rotations in three-dimensional space. My goal is for you to come away from this full experience understanding how exactly that works. And in the spirit of getting you playing with things from the start, I want you to start messing with these four numbers you see in the upper left. If you're on desktop, you can bring your mouse over them and either scroll while the cursor is hovering over it, or grab it to change it. And if you're on mobile, you can tap to interact. And as you change these numbers, you'll notice a couple of things. First of all, changing them causes the sphere that you're looking at to get reoriented. So this is what we mean when we say a given quaternion corresponds to an orientation in 3D space. And another thing you'll probably notice right away is that as you change one of these numbers, some of the other ones are forced to change as well. This is because the quaternions which describe rotation in 3D space are the unit quaternions, the ones where the sum of the squares of these four numbers equals 1. You might also be wondering about this second quaternion written below. And for the moment, I say don't worry about that one too much. In due time, when we understand why quaternion multiplication describes rotation the way it does, you'll know why this second one has to be there. But for this module, my only goal is for you to build an intuition for which quaternions correspond with which rotations. And depending on how brave you are to poke around and see some of what else is lurking within this applet, you might get to a point where things start looking truly strange. And that's because, in some sense, the image I have initially pulled up here of what seems to be just an innocuous sphere in 3D space is actually part of a much broader context of a four-dimensional hypersphere, which in later modules we're going to come to understand. But for the moment, for the purposes of just building up the intuition on which quaternions give which rotation, you don't need to worry about that. You can just think of this as an ordinary sphere in ordinary 3D space, no added frills or complications. One of the first things you might do to build a little intuition is notice how this sphere changes when you just change the I component to go from 0 up to 1, or if you do the same changing the j component to go from 0 up to 1, and likewise for the k. And if you want, please, by all means, pause my voice and just keep playing with that if you feel like there's good intuition to be built. But a slightly more generalizable way to understand which quaternions give which rotations will involve changing the representation here to a certain angle axis representation. So in this case, the real part is written as the cosine of a certain angle, and you can think of the three imaginary dimensions as representing a certain axis in three-dimensional space, just being scaled down by the sine of that angle to make sure that the whole thing is still a unit quaternion. So it's still just four numbers, where the sum of the squares of these numbers is constrained to be 1, but it's written in a different notation. So right now I have that axis set to be fully in the I direction, which you can see with this pink vector coming out of the middle. And what I want you to do is play with this value for the angle. Notice what it does to the sphere, and see if you can predict which angles correspond to which orientations. So the first thing you'll probably notice in doing this is that everything is rotating about the x-axis, which corresponds to the number I. Now, another thing you might have noticed is that there's a certain angle doubling thing that happens here. Notice, when we change this angle from 0 up to 45 degrees, the sphere is actually rotated 90 degrees. And if I push that up to 90 degrees, the sphere has actually rotated 180 degrees. That fact might seem a little bizarre, but it has to do with the idea that there's two quaternion products happening here. One by q from the left, and one by q inverse from the right, where in the angle axis representation, you can think of q inverse just by negating that angle. Just to give a little sneak peek as to why this angle doubling happens, for example, how putting 45 degrees in here gives us a 90-degree rotation, multiplication by q corresponds to rotating by 45 degrees, but altering that sphere in a certain way. Multiplying by q inverse from the right, where with quaternion multiplication, it matters which side you're coming from, involves continuing that rotation, but putting the sphere back in place. Don't worry if that doesn't make sense, I just want to give a little hint about what's going on. So the next thing I want you to do is change this axis by altering the values of either I, j, or k. And as you change one of those values, you'll notice that the other ones change, and the reason for that is to constrain it to always be a unit vector. It has to be the case that the sum of the squares of these three numbers equals 1. So you're playing a sort of continuous whack-a-mole. So go ahead, change that axis in some way, and then notice how the sphere rotates when you then change the angle. What you'll notice, and maybe this is what you'd expect, is that the values for I, j, and k determine the axis of rotation. As before, you have an angle doubling that goes on, so scrolling from 0 up to 180 degrees rotates the sphere a full 360 degrees. Feel free to stick around here and play around some more to build this intuition if you'd like. But to continue on with the next module, go ahead and exit out of this one or click on the link in the lower right.